Sampling distributions is a complex idea. It's when we know the truth for a population, and then we ask what could happen in a sample. Let's say we know 30% of UT students are freshmen. Well, then if we took a sample, what percent freshmen would we expect to see in our samples? Well, a little bit easy now. If 30% are freshmen, and I take a representative sample, I'd expect to see 30%. Let's say the average student has a GPA of 3.5 at UT. Well, if I took a sample of 100 students, what would I expect to see for the mean in this sample? Well, if the average student has a 3.5, I'd expect to see a mean of 3.5. That's not the whole chapter, though. There's variation in what you expect to see. Because not all the time will you see a mean of 3.5, given the truth for the population is 3.5, there'll be variation. How does that variation look? Well, let's answer those questions. Remember earlier on we talked about sample statistics are used to make inferences about a population parameter. Once again, this chapter is a little bit reversed though, because in this instance, we know the population parameter. We know the truth. We know 30% of UT students are freshmen. How do we possibly know that? Well, if we went to the registrar would have a list of all students. We could find out 30% are freshmen. We say, well, let's go ahead and test this idea. Let's go take a representative sample and see what we see, and see if we see results in line with 30% being freshmen. So to do this, we need to talk about the possible sampling distributions. The sampling distribution of the proportion would deal with categorical data. And I can't state this enough. When dealing with proportions, we are dealing with categorical data. This is a huge note you need to know. Think about this, the proportion of students who are freshmen. How would you ask that question? Are you a freshman? The proportion of students who love Taco Bell. Do you love Taco Bell? I do. So proportion deals with categorical data. Later on, we'll be dealing with quantitative data when we deal with the mean. The sampling distribution of the sample proportion asks, if we know the truth for some categorical question, like the percent of students who are freshmen here at the University of Tennessee, the proportion, let's say, is 30%, what might we see in a sample if we took a sample of 100 students? Once again, we know the truth. Sounds weird for statistics, because we're going to see, given a truth for a population, what are the expected samples statistics. Let's go back to what probability is. Probability, remember, is the probability of something happening. We can think about this as the proportion of something occurring, and we can also rewrite our equation from earlier, the number of outcome or successes, as x. So the number of times something occurs is x out of the total sample, very similar to other things we've done. If you have right here, for the University of Tennessee students in a sample, we saw 40 freshmen out of 100. Your sample proportion p hat would be equal to 0.40 or 40% if you express it as a percent. Important notation here on the screen. X is the number of successes. 40 freshmen were seen in the sample. N is the sample size. We took a sample of 100 students. P hat is the sample proportion, which means in our sample of 100, 40% of them were freshmen. The sample proportion is p hat, and its complement is q hat. As in our sample, 60% were not freshmen, found by 1 minus p hat. So we want to know about what could possibly happen for all theoretical sample sizes of 100. That sounds a little bit odd. Like our friend goes out and takes a sample of 100, another friend goes out and takes a sample of 100, another friend goes out and takes a sample size of 100. Well, do you think all of them will see exactly 40%? Might be a little weird that we saw 40%. But would they all see 40%? It'd be even weirder than us seeing 40% if 30% of the students are freshmen. So no. Unless they talk to the same exact students or get really lucky, they wouldn't see the same exact results with what they get in a sample. But however, there would be some similarities because we would all expect to get the same thing. If the truth is that 30% of UT is freshmen, if it is, then that is P. And you expect in your sample, that's how this is read, the expected sample proportion would be the true proportion. If 30% of students are freshmen, I expect to see 30% in my sample. The expected sample proportion is equal to the truth. And this is what we will center our distribution at, which is mu. Now, mu is generally used for quantitative data, but once again, mu right here means expected in this instance. So the expected sample proportion is equal to 30%. What about the variation? Well, the variation is going to be the proportion who are freshmen times the proportion who are not freshmen over the amount we sample. And this will lead to less variation in the distribution if we take larger sample sizes. Think about if you only take 10 students, there's going to be more variation. Well, you could have like 60%, or you could have like, 50, 60%. And we would also not pass one of our conditions coming up here shortly, so you wouldn't even want to do it for such a small sample size. We can find out the standard deviation of this distribution. The standard deviation of the distribution would be P times Q over N square root, that's not N square root. So let's try it again right here one time, because that's too big right there. P times Q over N, there we go, I think I multiplied, square root. About 4.6%. So 4.6% is going to be the standard deviation of the sampling distribution of the sample proportion. So we would expect some variation of about 4 to 5% around the mean of the data. And how can we write this then? As a normal curve. So our distribution should be normally distributed. The sampling distribution of the sample proportion, what we expect to see when we take a sample of students to see if they're freshmen, is normally distributed with a mean of 30%. And then we found the standard deviation of 0.046. And then we can draw the normal curve. So think about this. Was our 40% odd? What we saw in our sample, was that an unusual occurrence? The answer is kind of. Why? Well, remember, mu p hat, which is the mean of the sampling distribution, is equal to 30%. That's the truth, because p was equal to, and p is what goes right there. That is p, the truth. So if it's true that 30% of students are freshmen, I'd expect to see 30%. Notice where p is at the center of the distribution. Most likely thing to see. Now we go up one standard deviation right here. And going up one standard deviation, look where you're at. 0.346. Go up a second standard deviation and we get 0.392, which makes this 40% a little more than 2 standard deviations above the mean. We can just see it visually right now, but if you go to z-scores, you can figure it out mathematically here and see that it's a little more than 2. And let's show it. Remember, the z-score formula is going to be observation minus mean over standard deviation. So the observation is 0.40 minus the mean of 0.30 over the standard deviation of 0.046. And then that is equal to, it's going to be about 2.1-ish. Let's find out right here. So 0.10 is the top divided by that, and 2.2 when rounded. So we did a pretty good mark on there. The z-score of about 2.2, which is slightly unusual. This equation that you're seeing on the screen, I'm going to write it out as notation. I said observation minus mean over standard deviation. The observation is going to be the p hat, the observed sample proportion, minus the mean of the distribution, which is p over p times q over n square root, and that z-scores this. That makes that a z-score. Observation, which is going to be, we observe in our sample 40%. We subtract the mean of the distribution, which is mu p hat in this instance. And then we divide by the standard deviation, which was p times q over n square root. So highlighting these right here, there's the observed, which fell right there. Or rather, let's use the green, because that's where the observed is marked on the graphic. So there's the observed. The sample, or the mean of the distribution, is this mathematically, and that's this value right here. And then the standard deviation we'll do in a, trying to think of a color that will show up better. Do it in red right here. The standard deviation are those units right there. And doing that observation minus mean over standard deviation turns it into a z-score. So we can be like, that's a little unusually high. Like, that's a little weird. Did we get another weird results that we wouldn't expect? Well, that's one of them right there. And once again, knowing how to solve these out, especially if you have a distribution here of premature births, if 11.6% of births in the United States are premature, and we take a sample size here of 100 births, about what percent would we expect in that sample to see premature babies? Maybe we have a hospital that we think has an unusual high amount of premature babies being born, and we say, you know, they have 13% premature babies. So the proportion in the sample from the hospital was 13% premature. And so was this unusual right here for what we saw in the sample? Well, going to our data, the answer is, and you can look at it very clearly, no. 13% would fall right there, a p-hat of 13% observed in a sample. And we're pretending from the hospital, 13 babies out of 100 in the sample were born premature, where we know that the true proportion of premature babies in the United States is this. And then we figured out the rest of the quantities on the previous slide right here, showing you how we can get the standard deviation with p times q over n square root. If the true proportion is 16% are premature, that's what we would expect to see when we take a sample. And then we have the observed, which is what we actually got from the hospital. And I did make this up, that the hospital reports that out of the 100 babies, 13 were premature. So X is the number of successes, and N is the number of samples right there that we took. We can turn this into a z-score to figure out how odd it is. Once again, the z-score formula is going to be p-hat times, or excuse me, p-hat minus p, observed minus mean, observation minus mean, over standard deviation down below. That is equal to a z-score. Let's plug in the numbers. We observed 13% premature babies at the hospital. We expected, because this is the national average, we expected this, so we're seeing how far those numbers are away. We divide by the standard deviation, which is 0.032. It's on the previous slide. We can also figure it out. We can look at the distances down there. And as you can tell, it's a very small difference respective to the standard deviation. And let's find out mathematically, and let's tell someone the z-score is less than 1. So here's the observation minus mean over standard deviation. It's actually less than 1/2. My arrow needs to be a little bit further over here to show respectively the z-score of 0.43, I think it was. 0 point rounds to 0.44 rounded. That's a very kind of usual z-score, very common. And that's not a percent. The z-score tells us how many standard deviations something is above or below the mean. So the observation we saw from this hospital was not even a full standard deviation above the mean. It was very common for us to see right here. So we would say nothing to worry about at this hospital. Like, but it's high. It should be around 11%, 11.6%. You say, well, 13% isn't that high given 11.6 is what we expect, and it's from a sample size of 100. Now, if you increase the sample size to 1,000, look what happens here. You would drastically change the standard deviation. We can see that if we had taken a sample size of 1,000, we'd have to adjust this number to still make it 13%. That still would be a p-hat of 13%. Going down here to the bottom equation, let's resolve this. You can see now the standard deviation would get much smaller. We'd still expect the same percent of premature babies, but now the standard deviation would be, let me take, whoops, got the 0. So there is p-hat. I'm going to go 1 minus p-hat real quick. 1 minus p-hat is p. 1 minus p is q times p times q over n, and then square root. And it is about 1%. Oh, it might not be unusual. We're going to just put this at 1% here. And it's about 1% variation. And it's actually going to be within 2 standard deviations still. It would not be unusual, and we could redraw this down here and just put in our 1% by going here. So now we would have landed between 1 and 2 standard deviations, and you can work this out mathematically. We're just rewriting the curve with the new standard deviation for a sample size of 1,000. So once again, we need to make sure to solve these equations, know how to plug the numbers into them, because you will be doing things like this on the test if you're taking Stat 201 with me or many other instructors. So we have to know that the standard deviation shows us the variation around what we expect. And now with this new larger sample, we got the same result. And now our p hat lands further over the 13%, lands all the way here. And it's actually not unusual yet. It's a z of about, I think I can figure that out. Z of about 1.4. Well, not unusual. It's more unusual, but not reaching the bounds of very unusual or slightly unusual at 2 standard deviations. And I prefer to say 3 is very unusual. Now, easy one would be, what if there was 18%? Well, if there was 18%, you're off the charts. You'd look at your data right here, and someone's like, well, this hospital had 18%, so that's not unusual, right? And say, no. With 1,000 babies, 18% would be insanely unusual. It's completely off the chart. So the z-score there doesn't count anymore. We could take the data of the sample proportion of the hospital was 18% minus what we expect over the standard deviation of p hat right here. And let's go right here and find out 18% minus the mean divided by our rounded 1%. And that's going to be, I believe, 6.4. We'll double check on the calculator just in case. And this would be an extremely unusual occurrence. So yes, 6.4. And you can see it visually here because it's completely off the curve. Would be way over there. This is something you'd say, what's going on? Is there like a unit at this hospital that helps out with this? Because we're having a lot more premature babies. And it could be people go to that hospital because they have a really good premature team. And the hospital is kind of an unusual hospital via what we would expect given the population of the United States and premature births. So with this right here, there's lots of ways to do this data and lots of examples we can do. But we need to know the conditions for why we are doing this and if we can do this. And there are going to be 3 conditions around the central limit theorem. Now, the central limit theorem states that as we get larger samples, our data will have 2 things happen to it. It'll become more normal and tighter. We get better samples when they are larger. So the 2 things are more normal, and 2, tighter. Well, you actually just saw the tighter part of it because think of the formula we just learned. When it becomes tighter, we're talking about the standard deviation. There's less spread up to the data. So you have p times q over n square root. And as we increase and get larger samples, the tighter is because you're dividing by n. The standard deviation gets smaller. Now, what happens to the mean of the distribution? The mean of the sampling distribution of p hat is equal to p. There is no sample size in this equation, as in nothing happens to the mean. Notice in the graphic we just drew a second ago, the only thing changing about it when I changed the sample size was the standard deviation got smaller, i.e. tighter. We'd have to rewrite this right here to 1% for the sample size of 1,000. So as we increase the sample size, it'll become more normal and tighter. We need to meet our conditions right here. 1, were we taking random babies from that hospital? Well, hopefully we were, because that's the first condition. We have to say we're taking a random sample, or we have to know that we're taking a random sample of the data. 2, did we take less than 10% of the population? Well, we took 1,000 births. 1,000 children were sampled. Is that less than 10% of all babies being born? Yeah, I'd say so. We want to ask, what is the size of our population? How many babies are being born a year? So we could say out of a babies born a year, is this less than 10%? I would say millions. So as we said millions, let's just say 1 million, which is way underestimating. If we just said 1 million babies are born a year, way underestimate. We could then take our sample of 1,000 and ask, is it less than 10%? So you would need to think of a theoretical number. You could go on a low estimate, 1 million babies born a year, way low. It's probably like 50 to 70 million babies born a year, but this is an extremely low estimate. And then you would divide these numbers right here. You can cancel out some zeros. You notice we took at most 1,000th of the population. We have to take less than 10%. We took, and this is lowercase n over capital N, And if this is less than 10%, we're good. It mathematically is going to be this, which is way less than 10%. So once again, to check this, think about how big is your population. Some questions just say it. A question that would say University of Tennessee has 32,000 students. We go out and sample 100. Well, if we have 32,000 students and we sample 100, we can just plug our numbers in, see if it's less than 10%. 100 students out of the 32,000. Is this less than 10%? And we will definitely get that this is less than 10%. Solve your mathematics out, reduce decimals. It is 1/32, which is going to be, I believe, 0.003 125. It's got to be even smaller than that, right? Or I deleted one too many zeros, that's why. I think it's 0.3125. Let's check on the calculator. And we took a fraction of a percent. And we'll do the actual 100 divided by, there we go. Oh, it's even more zeros. Wow. More zeros. Very, very fraction of a percent. Or I actually typed it in wrong, I think, 100. That's why I was like, there we go. It's exactly what I said it would be. So once again, this is why I solve things in my head, because it's very easy to type things wrong on the calculator. Reducing zeros, getting a good estimate, and then doing in the calculator, a good way to check your work. And this is less than 10%. If you solve it out and it's less than 0.10, which is 10%, this means you've taken less than 10% of your population. The last condition right here is the success-failure condition. And the success-failure condition means we need at least 10 successes, at least 10 failures. Be careful, because when you do the 10% condition, you want less than 10%. It actually gets into a more complicated math theory on oversampling populations. It is better to have larger samples, but if you oversample, there are corrections we need to use, and this formula that we use in class right now doesn't have the corrections. But the success-failure condition is getting more than, or at least 10 successes, at least 10 failures. If you have exactly 10, that's all right. What do we mean by successes and failures? Well, successes is actually X. X is your number of successes in a sample. But in this instance, we're talking about how many successes do we expect. So we have NP hat, as in, if 25% of UT, 30, we said 30 earlier, if 30% of people at UT are freshmen, and we sample 100 students, how many freshmen would we expect? Well, NP. So we go right here and do 100 times this, and we would expect 30 freshmen. So if there are 30% freshmen, which is the assumed truth, or what we say is true from the registrar, we take a sample size of 100, we would then go and multiply the truth for the population by the sample size we are taking. Now, this is not saying we will get 30 students. It's saying who are freshmen. It's saying we would expect to get 30 students who are freshmen. So this is the expected amount of successes from a sample size of 100, where the true proportion of freshmen are 30%. Well, then how do you do failures? Well, the easiest way to do failures, in my opinion, is just to subtract this value out of the total. Because if you expect 30 freshmen, you'd expect 70 not freshmen. You can also go in here and change this to Q. So if we change this value right here, you can do the other equation, which is just going to solve out to 70, and we'll put in here Q, which is the complement of P. If P is 30%, Q is 70%. So N times Q, 70% right there, and we'll get 70. So we'd expect right here 70 not freshmen in our sample of 100. Why does this pass? Both values are greater than 10. Since we expect at least 10 freshmen and at least 10 not freshmen, 30 and 70 respectively, we now pass the condition, and we can say that we can now do the sampling distribution of the sample proportion. What does this mean? If you pass all the conditions, this is a huge note, you can now use the normal. If you pass all the conditions, you can now model it using the normal. The whole idea of using the normal requires you to have random data. Less than 10% of your population has been sampled. You have at least 10 successes, at least 10 failures. Remember earlier on, I said something out, we had a sample size of 10. I was like, well, that probably wouldn't be good enough because we wouldn't pass one of the conditions. So you must meet the conditions. randomly collected data, less than 10% of your population is sampled, and you must have at least 10 successes, at least 10 failures to do this right here. We could then say, as we did for the previous questions, with a sample size of 1,000, we figured out that the mean was P right here, and then the standard deviation was this, and we modeled it. We changed the question a little bit to figure out those values, and we modeled it with the normal. With the previous data entered in, well, now it has 925, and we can go back through and resolve. If you want to solve the standard deviation for 925 live bursts collected, go ahead and take the P right here. P is equal to 0.116. Find Q. Q is equal to 0.884. And then plug in P times Q over N square root. And N is equal to 925. We can look here visually, and we should get about, notice how this is close to 1,000. It's going to be a little bit larger of a standard deviation than my sample size I took previously, and that's the distances right there. Try solving this mathematics out. Understand what the standard deviation is. It tells us the variation for what is expected, and we definitely have a way large enough sample size right here. We have a large enough sample size for enough successes, enough failures. 925 children being sampled is less than 10% of the live bursts. And hopefully this is a random sample right here that was taken, thus we passed the conditions. So with this, we now get to the last topic to talk about here, which is another big one. We have right here, what if we have quantitative data? And this leads us to the sampling distribution of the sample mean. Let's change this right here. The sampling distribution of the sample mean. Previously, we were talking about, is a child premature? What about if we asked, what is the average weight of a child? That's a quantitative question. So the sampling distribution of the sample mean is for quantitative data. The sampling distribution of the sample mean is for quantitative data. I can't stress that enough. And when we do this, we have conditions for it. The first condition is going to be random. We randomly select the babies once again. Second condition, the babies are less than 10% of the population. We already know this, right? Well, the third condition is different. Now, we have a large enough sample size. This one's a little bit more confusing. What does it mean? Large enough condition means large enough sample size. As in, if the shape of our data is normal, we only need a sample size of 1. What N needs to be, this is the shape. If the shape of our data is skewed, we need 25. If it's heavily skewed, we need 100. There's the numbers down below. So if it's normal, we only need 1 observation because it's normal. If it's heavily skewed, we need 100. If it's skewed, we need 25. Now, these are words we're using subjectively, but remember back to the central limit theorem, that the larger the sample we take, the more normal the distribution will become. Now, here's a huge thing to write down. This doesn't change the shape of the original data. So the original data up here will stay the exact same shape. What changes is the sampling distribution of the sample proportion becomes more normal, or the sampling distribution of the sample mean becomes more normal. So as we get a larger sample size, the sampling distribution becomes more normal. As we get a larger sample size, the original distribution stays exactly the same. I can't state that enough. As we take a larger sample, our sampling distribution becomes more normal. As we take a larger sample size, the original distribution where you're taking it from does not change in shape because we can't change it. It's just a distribution of baby weights. Maybe they're right skewed, that some babies are generally have a weight down here, and then there's some really heavy babies. We're not going to change the shape of that. We're just going to change the shape of the sampling distribution of the sample mean becoming more normal and tighter. Let's look at some of the equations for this and how we find this. First off, here's the original data. As we said, Very, very, very right skewed. Sample size of 10, more normal. Sample size of 50, even more normal. And at a sample size of 100, we would probably achieve some sort of normality. And that's the goal right here, that as we get a large enough sample, it's normal enough. Now, it might not be perfect. It'll always go more and more and more and more normal as we get larger and larger samples, because remember the two things of the central limit theorem? As the sample size increases, the sampling distribution of the sample mean or proportion will become more normal and tighter. So we'll see this distribution. You notice the number line down here goes to 6,000 to 1,400. And then over here only goes from 8,000 to 1,200 because the standard deviation is getting smaller. The mean is staying the same for the distribution. The parent distribution, where it comes from, the original data, the population, is not changing at all. It's staying the same. So as you saw for the previous section, when we find the mean for the distribution of the sample proportion, it's the true proportion. The mean for the distribution of the sample mean, or the expected value, is equal to the mean. If the average baby weighs 8 pounds, I'd expect on average in our sample to see an average of 8 pounds. So this would be read, we know the truth for the average weight of babies in the US is 8 pounds. Then over here, we would say, bees look bad right there, there we go. Then we would say, I would expect to see in a sample, the sample mean, to be equal to 8 pounds. And you literally just take this number right here and plug it right there, because that's the mean. This is the mean. And we're saying the expected mean of a sample of babies we take when we look at their weight is 8 pounds. If you were to say the average student has a 3.5 GPA at UT and I talked to 100 students, what would you expect to see? Well, then the mean is 3.5. That's the truth. If I talk to 100 students, I expect to see 3.5. What about the standard deviation? Previously, it was P times Q over N square root. But P is only for proportions, like successes and failures. And so now we have to use the true standard deviation over the sample size. We still have sample size in both equations, and look, it's on the denominator, which means as sample size increases, standard deviation gets smaller. So it's a fact for both of these that as you increase your sample size, there's less variation in the data, which is one of the central limit components, that the distribution is going to get tighter. We can see a tighter distribution when the sample size is larger. You have to take your original population standard deviation, which we know for these examples, like the variation. Let's say students have GPAs that have a mean equal to 3.5 with a standard deviation of 0.3. It is right skewed, and we sample 100 students. Think about the formulas you already know right here, and let's practice. What we would do with this information is start by asking, one, did Brian take a random sample of students? Was his 100 students a random sample? I'd say yes, because I did. We'll just use that for the problem. Is 100 students less than 10% of the students of the University of Tennessee? Yes, because N over capital N is equal to 100 over 3,200, estimating right there, and that is way less than 10%. That's less than 10%. Do we have at least 10, is our sample size large enough? Because it's quantitative. I almost went to the wrong one. I was like, what is the notation I need to write down? And I was like, wait a minute, the wrong one. The third condition depends on which distribution you are doing. And so now we have to ask, is it large enough? Remember the question said it is right skewed. We'll say that the data is heavily skewed, and technically it should be skewed to the left, but I'll draw a right skewed distribution since I said it. Well, this is the original parent distribution, but because our sample size is 100, our sample size of 100 is, as we would say, large enough. So if the data is skewed or even heavily skewed in this instance, we have a large enough sample size at 100 such that the distribution of the sample data will be normal. So our data will actually get more normal and tighter around it right here. That's the parent, not P for proportion, but our distribution will be more normal and tighter around the mean of the data. So if this was the mean right here, it'll be more normal and tighter. The mean is going to go towards the right skew in this instance, and it should be nearly normal in this case. So now we need to take the data I just said, which was a mean of 3.5, a standard deviation of 0.3, sample size of 100. We know that the expected mean for the sample mean, or the expected sample mean, is equal to 3.5. Just plug in your original mean. It does not change. We know that the standard deviation, or the variation for what we would expect to see in the sample mean, is equal to the original standard deviation of 0.3 over square root 100. And yes, I did use nice numbers for that reason. And then we might say, would it be weird, this is where people usually get it wrong, to see a sample mean of 3.7? Would a sample mean of 3.7 be weird? Take a moment, write down these numbers. You can pause the video right here and write this down and solve it. Would 3.7 be weird? 3.7, a sample mean of 3.7 from 100 students, be weird? The answer is yes. You might have thought that we were talking about the original distribution. Well, the original distribution isn't normal, so we shouldn't even use the normal technique. If you went here and put your 3.5 and then went up to 3.8, you'd say 3.7 is right here. That's not unusual for one student to have a 3.7. But what we are talking about is not the one student, we're talking about the mean. Is this mean unusual? And the mean for 100 students being this high is very unusual. You draw out your data here, you can see that the mean of the sampling distribution is still 3.5, but its standard deviation is only 0.03. Notice how it's changed right here. And so that is the units we're going up, and you'll get that this is 3.53, and you can start to see you're not going to reach 3.7. So 3.53, 3.56, 3.59. We can go in here and solve for how unusual it is by doing observation minus mean over standard deviation. Observation minus mean over standard deviation. The observation of 3.7 minus the expected mean of 3.5. This once again just finds the distance of how far these quantities are away. It's off the graphic, we can't see it. Then we divide it by the standard deviation to put it in units of standard deviation. And this should be, I think, 6.66. So 6.66 standard deviations above the mean. So this would be very unusual. Did we go to honor students or something? Or did we go to, like, I don't know. I mean, who has high GPAs? Not me. So with this right here, this would be a very unusual occurrence to see in a sample of 100 students when we expect a 3.5 average GPA. Big thing right here. These questions only come with practice. Knowing what these things mean is writing down the notation, understanding what the questions are asking you to find, practice the questions. If I have any advice to give you right now, it's to sit down and do practice questions. Come up with your own questions. Try this. Let's write 2 practice questions to finish. First off, we know that 80% of students at UT love Taco Bell. Was it weird that our friend found only 60 out of 70 students loving Taco Bell? Check the conditions, find the z-score, and find the probability of more than 60 out of 70 in a sample loving Taco Bell. Now, the issue is you might have to go over and use an applet to do this. Right here, we can see, let's go over to our applet from Adam Spanbauer. We'll pull up the applet right here. Let's go check it out. We're still using the normal curve right here, so we have the normal curve applet. And if we find the z-score, we could simply go above. For any of those problems, especially the one we just did, the probability of seeing something above 6.6 standard deviations above the mean is going to be 0. We can solve this question that we've been working here by going over here and taking a look at it and thinking about what we have. Let's do a quick solve of it and use the applet to show the answer. More practice right here for you right now, then we'll do another one. So here we are with let's mark the notation. We know this, so I don't know how we know that, but apparently we have the sample size right here, which is n, and we have the x right there, which x over n, the amount of successes over the sample size, is going to give p hat, which is 6/7. And then we can find out if p is equal to 0.8, then q is equal to 0.2. We probably don't need q hat. This is p hat right here is 6/7, which I believe 7th is a 14th or 0.14. So that's about 0.86 or so, 0.86 or 857, I believe, rounded. 0.857. We'll check our math here in a moment. There we go. So with this, is this unusual? Let's try it. Do another new slide here. And let's draw the sampling distribution. First off, did we take our students randomly? Well, let's assume we did. The question should state that. We talked to 70 random students at UT. Next do we have at least 10 successes, at least 10 failures? We need to do NP is greater than or equal to 10, and NQ is greater than or equal to 10. Well, the N was 70, and the P was 80%. We should be good on that one. That's 56. And the N was 70 and 54, rather. So 54, those are both greater than. So 54 and 16. And notice how they add up to 70. Whenever you find NP and Q, you can do a check right here to make sure your numbers add up to 70, that you've done them correct. Also, did we sample less than 10% of the students at the University of Tennessee? We can do our check on that. To do that, we do N over capital N, and we've been assuming there's 3,200 students, and 70 is way less than 10%. So this means we can use the normal. By passing the conditions, you can draw your normal now. Let's draw the normal. What's even better is if you want, you can put your mu here and go up standard deviations. And the mean is going to be the truth. So the truth was, according to the problem that somehow knows the answer, at 80%. Then we do P times Q over N square root to get the standard deviation of this distribution. And be careful, it's not square root of N, it's P times Q over N square root, whole thing like that. And we'll go right here. And the standard deviation is this. It's about 4.7%. Watch this. Let's go over to the applet again. And by going over to the applet, check it out. We can put in the standard deviation right here, and we can put in the mean of 80%. And now we can see where we landed. If we landed at, and it was, we'll solve it here mathematically, 6 divided by 7, 85 right there, 85%. And we can go above. Now we're not using z-scores anymore. There it is. And actually, we landed right above the first standard deviation. Remember how above the first standard deviation is 16%? Well, we have about a 12% probability, and the z-scores between 1 and 2 z-scores. And we can draw this out ourselves, but notice how the applet shows you all the numbers down here by adding 1 standard deviation up. We landed at 85.7%, I think, so we landed right there. You can also z-score it to find out the answer, but problems like this, or trying to do this and knowing the notation, helps you solve all of these. We'll do one more example here and try to write the notation with me. So this will be another sampling distribution. This is of the sample mean. We know the average student at the University of Tennessee is 68 inches tall. Average UT student is, and we're not saying from a sample, 68 inches tall. How do we know that? Somehow we collected all the data. And so now, with a standard deviation of, let's say, 3 inches, and there is going to be a sample size of 64 students. Actually, let's go 25. The data is only lightly skewed to the left. Draw the sampling distribution, check conditions. Draw distribution is a sample mean from the 25 of, let's say, 71 odd. Okay. Be careful, people immediately start looking and they say, well, 71 is only 1 standard deviation away. Well, that's for one individual. We're talking about the sample mean. If you talk to 25 students, and on average, the 25 students had a height of 71, would that be odd? Let's first mark our notation like we do. Well, this all needs notation on it. And we have a double right there, so I'm just going to erase that because that's the sample size again. And so here is the true mean according to the problem. Here is the true standard deviation for the population. Here's our sample size, and here's the sample mean. Once again, this problem somehow assumes we know the heights of all UT students and the variation, which is the standard deviation. Okay, let's check the conditions right here first. So solving the problem. First off, did we take a random sample? Hopefully we did. Random samples needed for this. So if the problem says it, we did it. Problem should say it. And I'd write it in the problem. Question 2, did we take less than 10% of the population? Remember, we solved this with the sample size over the population size, and we took a sample of 25, divide that by the 3,200, and it's way less than 10%. Next, we have that is our sample size large enough? It's not the idea of success failure because we're dealing with quantitative data. We took a sample size of 25, and the distribution was skewed to the right. So with that, we first look at the shape, and we say, well, it's skewed to the right. A sample size of 25 is actually the requirement, so our sample size is large enough. The steps for checking large enough n are, what is the shape? Because you look at the shape, and my shape is this. The problem will probably say it's skewed, heavily skewed. If it's heavily skewed, you need at least 100. If it says normal, if you have 1, you're good. If it says skewed or lightly skewed, 25. So the more skewed it is, the larger sample you need. My sample size of 25 is large enough because my data is only skewed. So we pass all the conditions, which means we can model it with the normal. So going down here and modeling this with the normal, we need to know the quantities for the normal, which are going to be the mean and the standard deviation. So the mean for the distribution of the sample mean is equal to the original mean, and the original mean is equal to 68. The standard deviation for the distribution of the sample mean is equal to the original standard deviation over the square root of n, and that is equal to 3 divided by square root of 25, which is going to be 3 over 5, which is going to be 0.6. We draw this out right here. Now, this is for a sample of 25 students. What would we expect their height to be on average? 68 goes at the center because that is the mean. And remember, the mean is the distribution of the sample mean. The standard deviation does change, though, because it gets more tighter by a square root of n, and that is going to be the units by which we go up and down each time. We're only going to focus on the up here because we're thinking about is 71 odd. And if you notice, 71 is off the charts. So, and that'd be 69.8. It's off the charts. We can figure out how odd it is by using our formula, which will be the observation of y bar minus the true mean over the original standard deviation square root of n. Sorry about that, wrong square root. And so we take the observation of 71 minus from its 68, divide by the new standard deviation, which we found of 0.6. And this leads to a z-score of 5, I believe. So if we do 2 more standard deviations, you could think it goes up to 70.4. So we're over here-ish on the graphic. So is that odd? Oh my gosh, that is odd. That is off the graphic odd. So we are in the territory of something super unusual that is super unlikely to occur, and we've quoted the z-score for it to let people know that. Once again, the only way to get this chapter down is with practice. Try writing out your own problems as we did here, where you mark the notation, you check the conditions, you draw the distribution, and then even you could, and we didn't do it for this one, you could go to the applet, enter in the mean of 68, the standard deviation of 0.06, got too many zeros, and then you could look at the curve down here, but you should also try drawing this out, and you get the same data using the applet to solve these. Good luck, and let me know if you have questions.